In this video, we're going to talk about using lines to approximate things that aren't quite linear. So a graph has a linear model, meaning we have a straight line. But what that really means, or another way of saying that, is that it's changing by a constant rate of growth, or it's adding a constant. That's how you know something is linear. It's consistently adding a constant every time, and that's how it's growing, or it's growing by a constant rate, which is added. Okay, so they have us look at some graphs, and we're going to try to say, what if we used a line to represent this growth? I mean, we see all these wiggles, but if we kind of imagine like a smooth line, right, kind of going through this growth here, we kind of see it just visually growing through there. That line would represent this without doing all the ups and downs. We could get an approximation for each year. So they tell us, decide if it could be represented by a line. If so, define some variables and let's write an equation. Okay, so before we write an equation, let's remind ourselves when we talked about lines before, what we used was this idea that we would have like an initial value, some sort of starting point, right? And then we'd have our growth rate, which was a constant number that we're adding each time. Okay, so they gave us a little hint under here. So yes, I think the answer is yes, we can use a line to approximate this. For a for horizontal axis variable, instead of using years, use years since 2006. So let's use 2006 basically as our starting point. So we're going to approximate what that value is right there. And that's going to be our initial value. So our initial value then, maybe 381. I think that seems reasonable. 381. It's close to 380. It's a little bit above. I mean, I'm kind of treating it like it's only like one above. So I think 381 is reasonable. You could even do 382 if you really wanted to, but I think 381 is fine. Okay, so I'm going to go ahead then, since that's our initial value. This would be like t equals 0 then. I'm going to use t as our variable. Okay, so t. And t equals 0 is starting in 2006. So 2008 would be t equals 2, t equals 4. So this would be 6 years later, 8 years after 2008, 10 years after 2008, and 12 years after 2008. Okay, so those are the values I'm kind of using for t here. What variable would we use for the y-axis? So why don't we call it, since it's atmosphere, I'll go ahead and call these A. 380 up to 405. And these are amounts of CO2 as parts per million. I don't know why I put the 405 there. Sorry. Parts per million. Okay. So we'll use A. And that's the CO2 in parts per million. And that would be T, which is time or years since 2006. That was based on their hint. Okay, so is the rate of CO2 levels approximately constant between 2006 and 2016? Let's show at least two calculations. So at 2016, here, I'm going to put a dot there. That kind of looks like it's partially closer to 405 than 404. So I'm going to approximate that then to be 403. So 403 in 2016. And I'm going to compare that to the 2006 amount of 381. So that is a distant difference So 4, grabbing my calculator, minus 381, let's see, 22. And that's over 10 years. So for a 10-year period, then that's 2.2. So it's growing. The CO2 levels are growing at a rate of 2.2 parts per million per year. All right. Show at least 2 calculations. I don't know what they're meaning by that, so I'm just going to ignore it. Because what I just found right here is my growth. That's the linear growth rate. So if I want to make an equation, then I'm going to take my initial value of 381. Into it, I'm going to add 2.2 every year. And that's going to result in the atmospheric measurement of CO2. So there's my equation. All right. Now this one's not as nice. I hope we kind of see that. If I had to kind of create a line in this, I'm kind of feeling like the line's going to have to do something like this, right? It's not going to be as good as the last one. I felt like a line actually did a pretty good job, but this one's definitely a little bit more off. Now, as you can kind of see, we're working with much smaller values on the y-axis, but all right, that's what we're going to work with. So what variable shall we use for the y-axis? Well, let's kind of do what we did last time. Let's get a starting variable here that makes kind of sense. Now, based on my green line, my 1880 may not be a good starting value. I'm almost tempted to use 1900. Yeah, I think I will. So T is going to be years since 1900. Make that judgment call. 1900 is a good cutoff. All right. So based on this, and that's a negative. So that would mean in 1900, we're getting our value to be approximately negative 0.4, right? So these are very small little amounts here. Okay, so for the vertical asymptote or axis, wow, we are talking about temperature. So I'm going to go ahead and call that T, capital T, for the temperature in Celsius. That is not how you spell Celsius. There we go. Okay. Is it approximately constant? Well, not really. So I think I'm understanding what they mean by showing 2 constants. I think they're meaning like grab a couple different values from 2 different data points. Now we just used the 2006 and the 2016 in the last problem. So those were the years they referred to. But in this problem, I'm going to use 1900. And I'm kind of feeling like 2000. It's not too bad. 1900 and 2000 isn't too bad. All right, so 2000 looks like it's crossing at 0.5. So those are the values I'm going to use. So I'm going to take 0.5 and I'm going to minus negative 0.4. So really that becomes plus, right? When you minus a negative. So that's 0.9. And then I'm going to divide that by 100 years. That's going to come out to a very small decimal of 0.009. And that's the change in the degrees Celsius. But what we've just found is the linear growth again. So it's growing by about 0.009 degrees Celsius each year. And I believe we're talking about the ocean is warming up at that rate. All right. So continue on the next page. Oh, okay. New example. What variable would we use for the, okay, so again, this is even worse. Our line is definitely not doing as good of a job, but that's okay. We could still kind of force it to work. All right. However, I feel a little better about my starting point here being the first number. So I'm going to go ahead and I will let 1980 be my starting point. So T is years since 1980. Vertical, since we're talking about sea ice, and there, so we'll just call it I for million square kilometers of ice. All right. So in 1980, here, I'm going to write this down. That's going to be my initial value. And that looks like it's 7 point, maybe 7.7. So 7.7 million square kilometers of ice. And then here, let's go to 2010 is not so bad. So 2010 would be less than 5. So how about 4.9? So 7.7 minus 4.9 minus 4.9 on my calculator, I'm getting 2.8. And let's see, that's a 90-year period. So divide that by 90. And that is giving me 0.0. Oh, I just realized, technically it's decreasing by this amount. So even though I did 7.7 minus 4.9, I started with the earlier amount and subtracted the later amount. I just realized I treated that like 1800. Wow, that's not 90. Wow, that's so sad. Okay, so start over. Let's actually reverse this. So 4.9 minus 7.7, that's a decimal. Because the starting number, I'm sorry, the ending number is 4.9, starting number is less. It's negative 2.8. And that is a 30-year period, wowzers, which is negative 0.0, we'll just say 0.09. So it's decreasing million square, 0.09 million square kilometers every year. And to write an equation for that then would be I equals 7.7 was our starting value minus 0.09 t. So for every year, it's going to decrease by 0.09, that square area of ice.